Great expectations. We're going to take a look at expected value. So expected value of a variable starts with a variable x associated with a sample space S, is T1 to TR, with a probability distribution of P1 to PR. Recall here S is going to be numerical. It's going to be tags, which are numbers or vectors. That means we may have to do some pre-processing, map the data to a subset of a vector space. And usually that vector space will just be Rn. Then the expected value of x, or E of x, is a linear combination over the vectors in S, where the coefficients of the linear combination are the probabilities in the probability distribution. Or in other words, the sum x equals 1 to r, t sub x, p of x. It's also known as the theoretical mean of x. Sometimes it's denoted by mu or mu sub x. For example, here are 6 outcome of a die, and notice we're going to tag that. Our sample space is going to be the numerical 1, 2, 3, 4, 5, 6. We're going to assume the die is fair, so each outcome is equally likely, so our probability distribution is all 1/6. Our expected value is 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3. This sum, and that's 21 over 6, and that's 7/2, or 3.5. Now this was the average of the sample space, but only because the probability distribution is uniform. An unfair die would lead to a different expected value. For example, let's use another probability distribution. Now 1 through 5 outcomes have a probability of 1/10, and outcome 6 has a probability of 1/2. Our expected value is 1/10 times 1 plus 1/10 times 2, and so on and so forth, up to 6/2, which is 15 over 10 plus 3, which is 4.5. So how do we interpret this number? Well, we're going to build on the axioms until we have a good interpretation. So suppose x is a random variable associated with some sample space S, in this case just on the real line. Suppose f is a function that's defined for each t sub x in S. So therefore we can say a new variable y is a function of x with a new sample space y1 to y sub m, where y sub x is f of t sub x. So this y is a variable just like x is a variable. It just happens to be the image of f applied to the sample space of x. The expected value, therefore, is the sum x equals 1 to m, y sub x, p of x, which means that the expected value of f of x is x equals 1 to m, f of t sub x, p of x. So consider the function, say, f of x equals x squared. Here y is equal to x squared. X squared means that our sample space for the function applied would be 1, 4, 9, 16, 25, 36, the squares of the original S. These are instances of y equals x squared. The expected value of x squared would be the sum of all the things in S divided by 6. Notice we're back to our fair die. That's 91 over 6. Equivalently, the expected value of x squared is the sum, x and s, of t sub x squared p of x, which is k equals 1 to 6, k squared times a sixth. Move a sixth out here in front. There's a formula for the sum k equals 1 to n of k squared. Insert that formula. We get 91 over 6. But again, a natural question is, what is an expected value? So we're going to use an axiomatic approach to establish properties of expected values, and then we'll use those to interpret and answer this question. The first property is linearity. So how do we prove linearity? Well, we're going to have a joint probability distribution because we're going to have an x and a y where our sample space S is pairs t sub x u sub y. The expected value of a function is defined like this. And now we can prove our theorem. So we write out the definition. We split it up at the sum and factor out the alpha and the beta. And notice now we are summing over the y in the first sum. That's going to give us a marginal p of x. And we're summing over x in the second sum, which is going to give us a marginal p of y. And now we have the expected value e of x plus beta times the expected value e of y. There's our proof. So we have linearity, some immediate consequences of linearity. Suppose f of x is identically 1. Then we're looking at the expected value of 1 is f of t1, p1 up to f of tr, pr. But they're all equal to 1. And the sum of the probabilities is 1. So the expected value of just the number 1 is 1. And in general, the expected value of a constant is that constant. And if mu is equal to e of x, then linearity says that the expected value of x minus mu is 0. Now we're also going to look at the variance, which is the expected value of the variable x minus the mu, that quantity, squared. So let's look at some properties for variance. So again, we've got a x associated with a set S with a probability distribution. The variance is the expected value of the quantity x minus mu squared. And we square that, use linearity. And notice that e of x is also mu, so we've got minus 2 mu squared. The last one is the expected value of the constant mu squared, which is mu squared. And so we simplify a little bit, and notice that we've got the expected value of x squared minus the expected value of x, that entire quantity, squared. So there's our first property of variance. What if we had variance of alpha times x? Well, we write out our use our first property. We can factor out an alpha squared, and having done so, we see that we get alpha squared times the variance of x. So the variance of alpha x is alpha squared the variance of x for any alpha in R. So if x and y are independent, then we can show that the expected value of the product is the product of the expected values. So we'll have a joint probability distribution for the x and the y. If they're independent, the joint probability distribution is the product of the marginals. So let's prove our theorem. So we take the expected value of x times y, which is the double sum over x and s and y and s of t sub x u sub y, p of xy, but p of xy is the product p of x, p of y. So now we bring the p of x through the sum over the y, and we've got e of x, e of y. For example, suppose x and y are associated with 0, 1, and half probability for both. In other words, we're flipping two fair coins. The expected value is a half for x, and the expected value is a half for y. If I've got x and y in 0, 1, then the pairs xy are 0, 0, 0, 1, 1, 0, and 1, 1. And when I take the probability distribution for those pairs, it's a fourth, a fourth, a fourth, and a fourth, because x and y are independent. If I take the product, then I'm going to end up with the xy is associated with the set 0, 0, 0, and 1, respectively. So the expected value of xy is a fourth, which is the product of e of x and e of y. So independence and variance, if x and y are independent variables, then the variance of x plus y, by our property 1 of variance, it's this. We can square out the x plus y quantity squared inside the first expected value, and we can then use linearity. We can also expand the square of the sum. Notice when we reorganize that we're going to end up with some cancellation because we have the variance of x, then the variance of y, but notice that e of xy is equal to e of x, e of y. So this is the variance of x plus the variance of y. By independence, that last term is 0. So the variance sum law in general says if you've got x associated with some sample space and a probability distribution, and if x1 to xn are also associated with x with the same probability distribution as x, in other words, they're identically distributed, and if x sub I is independent of x sub j for all I not equal to j, which means they're independently distributed, we get this theorem. The variance of the sum is the sum of the variances. Let's prove it. It's true for n equals 2. We showed that on the last slide. But for the n plus 1 case, we let y be x1 to xn, summed together. Then the variance of y plus xn plus 1 is, by our previous slide, the variance of y plus the variance of xn plus 1. But by our induction hypothesis, the variance of y is the sum of the variances, proving the theorem. So if we take a sample of a variable x, we want to take independent samples. So we have independent variables x1 to xn, each with the same probability distribution as x. Or in other words, we say x1 to xn are independent and identically distributed. Sometimes we abbreviate that IID. Each xi has the same mean mu and the same variance as x. The sample mean is defined to be the average of x1 to xn. So we've got an IID sample x1 to xn. Their average is called the sample mean. And notice it's also a random variable. It's also associated with a finite set. Each x has only finitely many things that it could be, and there's only finitely many of these x sub i's. So the sample space for A sub n is all possible averages of n samples. It's very large, but it's still only a finite set. So we can treat the sample mean as a variable. So if we have x associated with s and then the sample mean with another space, this L is much larger than the size of s. Then, for example, suppose we had a coin toss. Well, A2 would be associated with what are the possible averages you could get for tossing a coin twice. Well, you could get both tails, which would be 0, a heads and a tails, which would average a half, and both heads, which would be an average of 1. Same thing, A4 would be associated with all possible averages you could get from tossing a coin 4 times, and so on and so forth. So AN is different for every sequence of n trials. It has a probability distribution, which can be calculated from the probability distribution of x, but that's usually far too complicated. We like to use theory instead. So we have x1 to xn associated with s. This is an IID sample of x and the same probability distribution for each of the x sub i's. The sample mean is a variable. What is the expected value of the sample mean? Well, we take the expected value of this linear combination, and it's the linear combination of the expected values, but each one of those has an expected value of mu, and so therefore you get mu n times, and therefore the expected value of the sample mean is also mu, which is the expected value of x. The variance of A sub n, the sample mean, is the variance of this linear combination. But notice when you bring the 1 over n out, you have to square it, These are all independent of each other, so therefore you get the sum of the variances. But the variances are all the same. So if the variances are denoted by sigma squared, then you get n copies of sigma squared added together, which is going to mean you're going to get 1 over n times sigma squared. So the expected value of the sample mean is mu, and the variance of the sample mean is sigma squared over n. So one more item, let's look at Markov's inequality. Suppose we have y is associated with S, with a probability distribution of P1 to PL, where there's L elements in S. The expected value of y squared is the sum, y equals 1 to L, of u sub y squared P of y. But these are all non-negative coefficients inside the sum. So for an epsilon greater than 0, this sum would have to be greater than or equal to the sum where the absolute u sub y is greater than or equal to epsilon of epsilon squared p sub y. Why? They're non-negative, and there are going to be fewer coefficients in that final sum. We can factor out the epsilon squared, but notice now this is the probability of the event that absolute y is bigger than epsilon. So we get epsilon squared, the probability absolute y greater than or equal to epsilon. And this is known as Markov's inequality. We divide through by the epsilon squared, and we get the probability of absolute y greater than or equal to epsilon is less than or equal to 1 over epsilon squared, the expected value of y squared. Okay, that wasn't that difficult, but why? Why did we do this? Well, let's suppose that x associated with S has a sample mean a sub n, and remember, if mu is equal to e of x, then the expected value of an is also mu. And by the definition of variance, it's the expected value of an minus mu quantity squared. So the probability that absolute an minus mu is less than epsilon is 1 minus the probability that absolute an minus u is greater than or equal to epsilon. And that is greater than or equal to 1 minus 1 over epsilon squared of the expected value of a sub n minus mu squared. That's by Markov's inequality. But that's just 1 minus the variance of a sub n over epsilon squared. Which yields our first answer to what is an expected value. So this is our result from Markov's inequality. We also had shown that the expected value of x, we denote it by mu, and that the variance of a sub n is sigma squared, the variance of x, over n. So we substitute that in, and then we're going to take the limit as n goes to infinity. But notice that in the final limit, there's an n in the denominator, so that limit's going to go to 0. And you can't have probabilities greater than 1, so therefore the limit of this probability is equal to 1. And that's what's known as the weak law of large numbers. For any given epsilon greater than 0 for n sufficiently large, the average over a set of n trials of a random variable is almost certainly, in other words, probability very close to 1, within epsilon of the expected value e of x. What that means is even though the expected, sample mean is different for every set of n trials, we still have that no matter how small epsilon is for a sufficiently large n, a sub n is almost certainly no further than epsilon from mu, the expected value of x. So we might want to say, well, a sub n is approaching the expected value of x, but that's too strong. So we're going to explore intuitively next what it is that we can say. We're going to do what's called sampling with replacement. So if x is associated with S with probability distribution P1 to PR, our samples in IID trials of x resulting in these trials. The samples must be independent trials. Independence means each x sub I has the same chance of being t sub x for each x, as every other trial. So that means we have to sample with replacement. So once we've selected t sub x in trial xi minus 1, we put that t sub x back in S before we get the next trial x sub I. So each trial occurs as if no other trials have happened. That's our concept of independence. So the sample mean over n samples is also denoted by this E sub n of x. And it may look like this, or like this, or like this. But regardless, we know we can arrange this so that the T1s come first, the T2s come second, and then up to the TRs, which will be at the end. And there's going to be approximately P of 1 n occurrences of T1 and P2 of n occurrences of T2, approximately. And if we factor the n out, we can cancel. And that's approximately the expected value of x. But only if we have IID and only with a probability of 1. In other words, sample means are probabilistic. So if we have x associated with S with this probability distribution, P1 to PR, there's our sample mean, and we have to have independent trials that we're summing over for the sample mean. For example, if we had a fair coin, heads is 1 and tails is 0, then the theoretical expected value would be a half. But what if every trial was 1? Then A sub n would be 1 for all n. But if we have identically and independently distributed trials, then the probability of every trial being 1 is necessarily 0. So even though we could imagine all the trials being 1, there's a probability of 0 that it would actually happen as long as we have independence. So therefore, we can say that if n is large and the trials are IID, then the sample mean is approximately the expected value with probability 1. So if x is associated with these numbers, again, sample mean is the average over n samples. Expected value is the sum, t sub x, p of x. Notice it doesn't depend on the number of samples. It's what we would expect if we let n go to infinity. For example, suppose we had a class of 100 that took a test, and 30 of them had a score of 70, 60 had a score of 80, and 10 had a score of 100. So our probabilities, probability of 70 is 0.3, 80 is 0.6, and probability of 100 is 0.1. The expected value is 79. But let's take 1,000 samples. Notice we couldn't even do that unless we had replacement. So we sample and pull out a student, look at their score, put them back in, sample again, put them back in, and we do that 1,000 times. And here's the result. 70 occurs 313 times versus a theoretical expectation of 300. 80 occurs 580 times. 100 occurs 107 times. And our expected value for this, our sample mean for these 1,000 trials is 79.01. So we have theoretical, a variable x associated with a set S, whereas in the empirical, we're looking at trials of x. The expected value, or the mean, is the theoretical expectation of x. The sample mean is the average over some number n of trials. The variance is sigma squared, denoted sigma squared, and it's the expected value of the quantity x minus mu, that quantity squared. Sigma is sometimes called the standard deviation of x. The sample variance is defined similarly in that it's the sum over trials. 1 over n, I equals 1 to n, the quantity x minus the sample mean, that quantity squared. And sometimes It's denoted by S sub n squared, where S sub n is the sample standard deviation, which provides a second answer to what is an expected value. This is the strong law of large numbers. Given that all trials of a variable x are IID, the random variable, which is the sample mean of x over n trials, satisfies that the limit of the sample mean is equal to the expected value with probability 1. In other words, the limit of this empirical sum is equal to this theoretical expected value with a probability of 1. Now, we didn't prove the strong law, we just look at it intuitively, but for finite sample spaces, the weak law is sufficient for any rigor we might need coming from the axioms. So the law of large numbers also applies to functions. So we have our x associated with S, probability distribution P1 to PR. The law of large numbers says that the probability that this limit is equal to this expected value is 1. And if y equals f of x, then the law also applies to y. So we end up with this version of the law of large numbers. Thus, the law also implies that the variance, sample variance, is approximately the variance. In other words, the probability of this function of x of I is equal to the expected value for that function. That's what gives us that the sample variance is in some sense an approximation to the actual theoretical variance. So notice we can actually use this to define probability as a relative frequency. We just find a function f, a real valued function, and notice that the law of large numbers says that with probability 1, e sub n of f of x converges to e of f of x as n goes to infinity. And if we define a characteristic function of a set A to be 1 if that v argument is in A and 0 if it's not in A, then the expected value of that characteristic function of x, the sample mean, is 1 over n, the sum I equals 1 to n of the characteristic function of xi. But the characteristic function of xi is either 1 or 0. And that means that this sum is actually a count of the number of times that A occurs in n trials. So we define this to be C sub n of A, the number of occurrences of A in n trials. And therefore, our sample mean for the characteristic function is a count divided by the number of trials. That's called a relative frequency. The theoretical expected value, on the other hand, is just the sum over A of the probabilities, which is the probability of A. And therefore, the law of large numbers says that with probability 1, the probability of A is the limit as n goes to infinity of the relative frequency, the counts of the number of times in n trials that A occurs over n. So in summary, the axiomatic approach to probability is all we need to develop all of probability theory. We can develop the concept of expected value, justify, but haven't proven the strong law of large numbers. We did prove the weak law. And this in turn allows us to interpret and connect to applications the concept of expected value. Indeed, the applications of probability are quite often applications not of probability, but of expected value.